Good morning, dear coaches. My name is Georgy, and my talk on the topic how does the Lidov Kozai mechanism protect quadrantid meteoroid stream from chaos and chaos with Jupiter. Um, we know that the Quadrantids is one of the stronger meteor shower. The parent body of Quadrantids is only 200 to 300 years old and is associated with the asteroid 2003 H1, while the white part of the stream connected with 96 P much close. The asteroid is expected as German or recently extinct comet. Uh, in many works, the asteroid and quadrantids locate in resonance zone. In this work, we try to answer the following question: how does the Lidov-Kozai mechanism affect the dynamic evolution of simulated meteoroid stream of a quadrantids? How is the period in which the orbit can be regarded as stable long? That is the case with chaos of motion in meteoroid stream. In this experiment, we can find ourselves of rolling point, the first observation of a shower around 1835. The asteroid is the core of the stream. The asteroid orbit is stable on the time interval from 1760 to nowadays, according to parameter magnet. The method of stream modeling due to cometary velocity sublimation is widely well understood and was reported many times by many authors. All meteoroid ejection model to great extent share the same physical concept, although with a slight modification. The main idea of the method is that they generate ejection of some amount test particles at some point on the orbit of a parent body and following the evolution of them to the epoch of our choice. The simulated ejections of 500 model meteoroid at Peruvian passage of parent body approximately 1764, 1769, and our epoch. In this figure presents some variability of the orbital perimeter of a model of a quadrantid meteoroid stream by investigating the time values of equation of motion test particle space around the parent body. We investigate the orbital evolution of each ejected particles from the moment of ejection until nowadays. The perimeter magna a row of chaotic and regular motion to be separated and where predictable time of estimate. As see this figure, the perimeter magna linearly grow for half of the simulated particle of ejection um, moment pass through value 2. Unfortunately, the integration period of the vase when 400 years is too short to decide whether the considered set of orbit is regular, regime, or of orbit and chaotic and whale motion and predictable for longer time. Um, we found increase can be um, like this figure in the interval from moment ejection to 1900. In this interval, the increase monotonous parameter magna and mean value exceeded 2. It would apply the same conclusion as we see on the side, for example, that the orbit, the chaotic and further motion, the particle is unpredictable. However, in the interval from 1900 to 5000 time unit, the magna decreases and the behavior above a stable orbit. And in these figures show vibration the argument perhaps is and magnitude ascending known of a simulated particle orbit representative quadrantid meteoroids with period about 4,000 years. Also, exists an inclination not very exchanging energy with each other for some particles. Um, we demonstrate mm, this moment and this picture. Uh, on the left side, there is a particle that has chaotic motion, and the right side a stable motion. We may see along a period the um, vibration when increased mean value parameter magna test particles phenomenon and hence where orbit are chaotic. These chaotic simulated particles has many frequent calls and calls with Jupiter in the area where Hill sphere radius is displayed by a gray horizontal line. This stable simulated particle does not have um, frequent calls and calls with Jupiter, but after transition, the argument perhaps is from value 100 80 degree to 50 degree. Parameter begins to grow slowly. Uh, in fact, the evolution of stable objective particles exhibits a Kozai type circulation. In that swing in eccentricity and inclination approximately converse um, semi-major axis. Top left-hand side panel show the perpendicular dynamics of stable simulated particles lead to avoiding close encounters with um, uh, Jupiter. The value of the semi-magic axis changes slightly during the time interval displayed from the quasi-constant um, reverticals 1 for most to integrated time. On the other hand, the values intensity and inclination oscillate and alternating high eccentricity and inclination. The vibration um, argument or perhaps it confirms that this object is currently subject to Lidov mechanism. But where transition argument perhaps is from vibration around 180 to vibration around 0 and back, the parameter magnum begins to grow slowly. When particles were away from the Jupiter, the orbital rotation changes, only side becomes smooth and rings disappear. In our case, the reductive Kozai mechanism it work avoiding close encounters with Jupiter at the failure for stable ejected particles stop uh, and um, and, these simulated particles does not have many frequent close encounters with Jupiter and display clear episodic relative Kozai mechanism behavior. Now, uh, however, Wishes close encounters with Jupiter are not treated by Kozai feminism and can transfer particles away from Kozai trajectories over time, as can be seen from the figure for unstable ejected particles. In conclusion, I want to say in our analysis, the dynamical of meteoroid particles assumed to be erased from the asteroid reverted by complicated dynamical structure, a meteoroid stream with approaches Jupiter. Where increases parameter magna has been observed moment of changes with semi-major axis, multiple calls with Jupiter near Hill sphere what can be sources chaoticity. Gravitational perturbation from the Jupiter and frequent calls with planet bring up interesting drastic changes on orbital evolution some tested particles. The exit from the resonance Kozai contributed to manifesting of the geologic motion and certain particles. Simulated meteoroids inherit the dynamical properties of asteroid, but not all properties. Thank you for attention.